Hello everyone, welcome to my video on elementary differential equations. This is video number 15 of chapter 2. This is the last video on the topic of modeling with first order equations. In this video, we will consider the problem of air resistance. Here is the word problem. Let us read through it. So we are going to throw a ball, and the ball has mass 0.5 kilogram, and it's thrown upwards and with an initial velocity 10 meters per second, so that's going upwards. And this happens on the rooftop of a building, and the building, the height is 30 meters. Assuming now there is air resistance, and the air resistance is proportional to the speed, and therefore is the absolute value of velocity, and divided by 20. And the question here is to find the maximum height above the ground the ball would reach. So it would be actually useful to draw a diagram, like a sketch of a building. You can put a sketch of a building here, and then on the top, that's the initial position, and the ball has initial velocity going upward. And then we know by gravity it will slow down and reach certain height, and then it will come down and eventually hit the ground. Okay, so with that animation in our head, let's try to solve this problem. Let's define our variable. We call it capital S of t. That will be the position of the ball at time t. So the position will be m is in meter. And now we can assume upward to be the positive direction, and then the position would be the height of the ball above the ground level. So once the position is defined, then we can define the velocity, v of t, which is just the derivative of the position, so s prime of t. And then the acceleration can also be defined, which is again the derivative of the velocity. Okay, so let's adopt the positive direction to be pointing upwards. And then we can apply Newton's law. Newton's law says the force, total force on the object will cause an acceleration. In fact, the force equal to the mass times the acceleration. So what are the force that's applied on the ball? So first there is the gravitational force, which is pointing downwards. So it's negative. So I have negative mg. And then there is the air resistance with this as the amplitude. And then we know that the air resistance is always against the velocity. So it will always point in the opposite direction of the velocity. Therefore, we'll get negative v over 20 as the air resistance force, taking into account the sign of it. Okay, so treating this as the equation, we can divide both sides by the mass m, and then we have a equal to negative g minus v over 20, and then m. Okay, and then we see that now the acceleration is represented by the velocity. So taking the relation between a and v, so a is just dv over dt, then we see that we obtain an equation for the velocity. Okay, so since we are in the metric system here, then the gravitational constant is 9.8, and the mass of the ball is given, which is 0.5. Now let's put these numbers in, and we can write out an equation for v. v prime dv dt is, putting m is 0.5, we get negative 1/10 of v minus 9.8. Okay, and I can take out a 0.1 here. I will get negative 0.1 and then v plus 98. And we see that this is a first order linear equation. And we also see that this equation is separable. So there are various ways we can solve this. Okay, so here I repeat the equation in blue on the top, and let's solve this as a separable equation. So we'll move this factor to the left, so I get that, and then I move dt to the right, and then I integrate both sides. And then we see this integral gives me natural log, and this is a number, so I get a t multiplied on that, and my integration constant. Okay, and we can solve it actually explicitly. So natural log of this equals that. That means this equals exponential of this. So we get v plus 98 is exponential of this, which is exponential of the first term, times the exponential of the arbitrary constant, which is again an arbitrary constant. It's different, so let's mark it as c bar. Okay, and then finally we can move the constant term to the right and write an explicit expression for the velocity. Okay, now we can find the initial condition and plug that in to determine the constant c bar here. So what is the initial velocity? So at t equals 0, the ball is being thrown upwards with speed 10. So v at 0 is 10. So plug in t to be 0, this is 1, so I get negative 98 plus c bar is 10. That's my condition. And this allows me to solve for c bar, which is move the 98 over, just 98 plus 10, so it's 108. Okay, and then we can put the c bar back into the general solution, and we have the solution for the velocity at any time t bigger than 0 and before it hits the ground. Okay, so now let's find the position s as a function of time. Here we can use the fact that s prime equals v. Therefore, if v is given, then s is just the integral of the v. So let's plug in the expression for v. That's this one we obtained from the previous page. And then we integrate each term. This gives me a linear term, and the integral of the exponential function is the exponential function, and then divided by the constant exponent here. And then we have an arbitrary constant coming from the indefinite integral. And then again, that constant can be determined by using the initial condition for s. So initially the ball is on top of the building, so s at 0 is 30, the height of the building. So putting in t to be 0, and then you get just 1 here, and then we'll get 108 divided by negative 0.1, which give me this number, plus c. And then I can find the value c. Okay, so putting the c back into the solution, now we have the solution s of t, the position as a function of time. So with the v of t given and the s of t given, now we are ready to answer the question. That is the height, the maximum height of the ball. So let's find out first, at what time does the ball reach its maximum height? And let's call this time capital T. So one thing we know is at the maximum height, the velocity will be 0 because it will be changing the direction, go to the other way. So we want to find the capital T such that v of t is 0. Okay, so let's plug that in. So v of capital T is this expression, and we want this to be 0. So now we have an equation to solve to find capital T. Okay, so let's try to move everything to the other side. So we can move 98 to the other side and get this. And then we can divide both sides by 108, and then we get that. And then we have an exponential function alone. Then we know the exponent here is the natural log of this. So we get this. And then we can divide both sides by -0.1 and get the t is -10 of that, which we know this number is less than 1, so it's negative. So we can write 10 times ln of the inverse of this number, so 108 over 98. And then we know this is a positive number. Of course, you can hit the calculator and have it, but let's wait until the end. So once we have found the time when the maximum height is reached, to compute the maximum height, it's very simple. So Sm now is simply plugging in capital T in the expression of the function s. Okay, so let's evaluate. So t is that, and let's plug it in. And then we get this term, and then we get the exponent term where we plug in the t here and the constant. Okay, and the rest is just a little bit manipulation. Exponential ln cancels each other, then you get just that term. And then here probably it's safe to hit your calculator and find an actual number. So it's 34.78 meters. So remember, the building was 30 meters high. So actually the additional height you managed to throw is only 4.78, less than 5 meters. Okay, so for this problem, one could ask other possible questions. So let's discuss some. First, you could ask, find the time when the ball hits the ground. So to answer that question, we can go to the function s, because that's the position of the ball. This time th hit the ground time, at that time, s evaluate that shall be 0. And then we can be attempted to solve this equation. But then this s here is a nonlinear function, so it might not be so easy to solve it exactly. But it's a way. And then we can be asked to find the impact speed when the ball hit the ground. And this question could be answered once we have answered the previous one. That is, we have found t when it hits the ground. So you can simply plug that t into the velocity function and compute the absolute value of it, and that gives you the speed. Another question would be find the total distance traveled by the ball and when it hits the ground. So that we could actually already answer, because we know the maximum height, right? So we can just we can add up the maximum height with the height it traveled upward. So, and it would actually be 2 times Sn minus the height of the building. So this statement is not completely correct here. Here we were thinking of and the height is starting from the top of the building. Okay, so let's look at one more example. This is an example which would end into a nonlinear PDE. So here's the word problem. So we have a rocket sled, and it is traveling through a channel of water and being slowed by it. And we are given the initial velocity, and then we are also assuming that the acceleration, actually deceleration, it's a negative acceleration, satisfies that this a is negative 0.01 v squared. So it's proportional to the square of the speed. And we have three questions. 1, find the velocity as a function of t. And then 2, we want to find the distance traveled at any time. And then 3, we want to find the distance traveled when the speed is reduced to 10 meters per second. Okay, so we know that we'll have to set up our equation. So acceleration is just v prime. So we will know that v prime is negative 0.01 v squared. So immediately we have the equation. And the initial condition v0 is given from that. And we see that it's a nonlinear equation because the v squared term. But then we also see that it's separable, so we can solve it. So I will be brief in the solution because we know what to do already. So let's move v squared over and put dt here, and we integrate. And integrate of this gives me 1 over v, and then integrate this, give me that with a constant. And then I can take the reciprocal on both sides and get the explicit form. V of t is 1 over that. Okay, and then the arbitrary constant c can be determined by the initial condition. So v0, putting t to be 0, is 1 over c is 100, so c is 0.01. So we can find the solution now. Put in the c, 0.01, we get this expression, and we see if we multiply both sides by 100, it looks a bit nicer, so we'll clean up a bit and we get this expression. Okay, and that answers the first question. Now for the second question, the position s, we know s prime is v, and we also know s0 is 0, so to find s, we just integrate v. Here, knowing that s0 is 0, we can actually do a definite integral from 0 to t, because st minus s0, s0 is 0. Okay, and then let's call the parameter tau to say it's an integration variable, not the t here. Okay, plug in the expression for v, which we got here, and then we integrate this, which gives me 100 and natural log of tau plus 1, and where you set tau from 0 to t. So we see that when tau is 0, ln of 1 is 0, so we just get where the tau is t, so that's the solution. Okay, so this is a little bit different from what we are used to do. We are used to do an indefinite integral and then deal with the constant by the initial condition. So this is alternative way, that is, recognize the initial condition and then you can work out a definite integral immediately. Okay, so this answers the second question. Now finally, let's look at the last question. So we need to first find out the time when the speed is becoming 10. So let t bar be the time. So v at t bar is 10. So we plug that into the expression for v. V of t bar has to be 10. And we see that we can easily solve for t bar. and t bar here is 9. So you see 9 plus 1 is 10, and it solves the equation. And then to find out the distance traveled, and you just plug t bar into the solution for s and evaluate it. So which is here. So it's 100 times ln of 9 plus 1. And then you can hit your calculator and you find out the distance, 230.3 meters traveled by your slide. Okay, that is all I have to say for this example and for this video. And then we completed the topic of applications modeling for first-order equations. Okay, and next video we'll move on to a new topic. I hope you enjoyed this video, and I look forward to see you next time.